Welcome to session 7 of the Digital Electronics Problem Solving course on IEEE. I'm your instructor Sachin from the Indian Institute of Science. Since most students are not joining the live lectures, I've decided to record the videos and post them, and you can view them at your leisure. Last class we left off at problem 4.11. We'll continue from problem 4.12. Problem 4.12. Design a half subtractor circuit with inputs x and y and outputs diff and bout. The circuit subtracts the bits x minus y and places the difference in D and the borrow in B out. Part A. Design a full subtractor circuit with 3 inputs x, y and b in and 2 outputs diff and b out. The circuit subtracts x minus y minus b in I think they have made a mistake here. I would call this part A and call this part B, because part B is, yeah, this is more convenient. Solution to part A, we are trying to get a half subtractor. X and Y are the input bits. There is the difference output and the borrow output. 0 minus 0 is 0, and you don't need to borrow anything. 0 minus 1, you'll have to borrow 1. When you borrow 1, x will become 1 0, which is 2. 2 minus 1 is 1, so the difference is 1, and the borrow is 1. 1 minus 0 is, difference is 1, you don't need to borrow anything. 1 minus 1, difference is 0, you don't need to borrow anything. So the difference is x XOR y, and the borrow is x bar y. So the circuit can be implemented the following way. You have x bar, then y, x XOR y is the difference output, and x bar y is the borrow output. That's a half subtractor. A full subtractor, what does it do? It will subtract bit y from bit x, but if there is a borrow from a previous operation, suppose you have two digits, let's say in decimal subtraction, 21 minus 13, you borrow 1 from the tens place, and that will become 11. 11 minus 3 is 8. Now when you're doing the subtraction in the tens place, this from 2, you're actually doing 2 minus 1, but another 1 has been borrowed from the tens place. So there's a borrow in, that is a borrow from the previous operation that you need to subtract from the tens place. So that the circuit that does that in binary is the full subtractor circuit, and the truth table of a full subtractor would be as follows. There are 3 inputs, so there are 8 2 power 3 input combinations. Each of which will give some particular output. 0 minus 0 minus 0 is 0. 0 minus 0 minus 1 is 1 with the borrow 1. 0 minus 1 minus 0 is a 1 with a borrow 1. 0 minus 1 minus 1 is a 0 with a borrow 1. 1 minus 0 minus 0 is 1 with borrow 0. 1 minus 0 minus 1 is 0 with borrow 0. 1 minus 1 minus 0 is a 0 with borrow 0. 1 minus 1 minus 1 is a 1 with a borrow 1. That is 1 minus 1 is 0. 0 minus 1, you will have to borrow 1, then this will become 2. Subtract 1, you will get 1. So its difference is 1 when you borrow 1 from the next higher place. This is the truth table. From this, you can simplify using a K-map, and you will get the difference is x XOR y XOR b in, and the borrow is x bar be in plus x bar y plus y be in. And the circuit will be the difference output is XOR of x, y and b in. For the borrow output, it's a sum of three AND terms, and the three AND terms are x bar b in x x bar y and y b in. Give me a minute. I'll go to the restroom and be back. I'm back. So we have completed one problem. We'll move on to the next problem, problem 4.13. Let me write down the problem. From here on out, I won't be reading out the problem out loud. I'll just write the problem and I'll tell you the solution out loud. There are five parts, five different value. Let me draw the circuit for you. So this is a simple adder subtractor circuit where each of these blocks is a full adder. That is, it will add 2 bits with an input carry. So suppose there is no input carry, we can't give an input carry in this particular circuit, and we want to add two 4-bit numbers. Then we give 0 to the input M. What will happen then? The output of each of the XOR gates, if Bi is one of the inputs, where I is the index 0, 1, 2 or 3, output of each XOR gate is Bi XOR M. If M is 0, it's Bi XOR 0, which is Bi 0 bar plus Bi bar 0, which is nothing but Bi. So the two inputs to each of the adder is Ai Bi, and the carry in initially C0 is 0. So it will perform a 4-bit binary addition. Suppose we want to perform subtraction, then we will give M is equal to 1, and when M is equal to 1, M XOR Bi for any index 0, 1, 2, 3 will be Bi complement. So you will get the ones complement of B3, B2, B1, B0. To do subtraction, you have to take the 2's complement. So for that, we will have to give an input carry of 1. So the 2's complement is nothing but the 1's complement plus 1. So when M is 1, input carry C0 is also 1. And this particular circuit will perform the subtraction operation then. And in either case, if the C3 and C4 if are not both 0 or they are not both 1, then there has been an overflow. That is, if you are adding two 4-bit numbers in 2's complement representation, suppose you add your in 2's complement representation with 4 bits, you can have 2 power 6, 2 power 4, which is 16 combinations, so you can go from -8 to 7. So if you add two sevens, you'll get a 14. which is obviously out of range of your representation. So you can't represent a 14 in 2's complement 4-bit number form. Similarly, if you subtract 2 -7, say and get a -14, which also can't be represented in 2's complement 4-bit number form. So there will be an overflow. So that overflow, whenever it occurs, either C3 is 0, C4 is 1, or C4 is 0, C3 is 1. You can verify that from the truth table. So this is the circuit. Now they're asking what will be the output. Okay, the question here is, in each case, determine the values of the 4 sum outputs, carry C and overflow V. So we have to write S3, S2, S1, S0, carry and overflow. First case, M is 0, so it's an addition. You're adding 7 to 6, it's 13. The sum you will get is 1101. So it's 0111 plus 0110. 1 plus 0 is 1. 1 plus 1 is 0 with 1 carried over. 1 plus 1 plus 1 is 1 with 1 carried over. So 1101. Sum is 1101. Carry out is 0. Both of them are sorry. Here C3 is 1. This is C3 and carry out is 0. So 0 XOR 1 is 1. So there is an overflow. You can go only up to 7. You can't represent 13. Similarly for part B, we are adding 8 and 9. But in 2's complement representation, these numbers are not actually 8 and 9. So whenever there's a 1 in the MSB, it's a negative number. So you'll have to take the 2's complement and it will be the negative of that number. What I mean is, if you have 1 triple 0, 1's complement is 0 triple 1, plus 1 is the 2's complement, which is 1 triple 0. So this number is actually -8. And 1001 is 0 1 1 0 plus 1 is 7, it's minus 7. So let's add and check what we get. 1 0 0, C3 is 0, C4 is 1. So C3 XOR C4 is 0 XOR 1, which is 1. So there is an overflow, there is a carry out, and the sum is 0 0 0 1. So you should have gotten minus 15, which can't be represented with just 4 bits. C, D and E all have m is equal to 1, so they're all subtraction operations. And subtraction operation happens in the following way. 1 1 1 1 1 0 0, A is 1 1 0 0, B is 1 0 0, which is complemented, you will get 0 1 1 plus 1. So 1 plus 1 is 0 with 1 carried over. 1 plus 1 is again 0 with 1 carried over. 1 plus 1 plus 1 is 1 with 1 carried over. 1 plus 1 is 0 with 1 carried over. C3 C4 XOR is 0, so there is no overflow. And so this number is minus, this number is minus 4, and this number is minus 8. Minus 4 minus 8 is 8 minus 4 is 4. So it's within the desirable representable range, so there is no overflow, which makes sense. Carry out is 1, result is 0 1 0 0. Similarly, for parts D, you have 0 1 0 1 and 1 0 1 0 is B, which will be complemented to 0 1 0 1, and 1 is added. So there is an overflow, there is no carry, sum is 1 0 1 1. Final part 0 minus 1. No overflow, no carry, sum is 1 1 1 1. Okay, that had a lot of parts, a pretty lengthy problem, but pretty simple. Let us go to problem 4.14. Let me let me draw figure 4.12. Or maybe I could just alright. So the circuit is a carry look ahead adder. There's an XOR operation at the inputs and an XOR operation at the output. So the first stage is P3, G3, P2, G2 generation of the parity and generator of PI and GI. And the next part would be carry look ahead generator, which generates C1, C2, C3, C4 using P1, P0 to P3 and G0 to G3 and C0. Third is the parallel XOR stages, which generate the outputs S0 to S3. So for the first stage, the XOR operation will take 10 nanoseconds and the AND operation will take 5 nanoseconds. So by the time the XOR is completed, AND is already completed. So the limiting factor is the propagation delay of the XOR operation. So the first delay is 10 nanoseconds. So the for carry look ahead, you can look at the circuit, look up the circuit yourself. For carry look ahead generation, so this is stage 1, this is stage 2, this is stage 3. In stage 2 there are one parallel AND stage and a parallel OR stage. Parallel AND stages will take 5 nanoseconds. Parallel OR stages will take 5 nanoseconds. So second stage delay is 5 nanoseconds for the AND and 5 nanoseconds for the OR, which is 10 nanoseconds. Stage 3 we have again XOR gates which give 10 nanoseconds. So total delay is D1 plus D2 plus D3, 30 nanoseconds. Problem 4.15, derive the two-level Boolean expression for the output carry C4 shown in the look ahead carry generator of figure 4.12. So we have for the carry look ahead generation, C1 is G0 plus P0 C0 and Ci plus 1 is Gi plus Pi Ci. Using that we can write C2 is G1 plus P1 C1, C3 is G2 plus P2 C2, C4 is G3 plus P3 C3. Then substitute for C3, G3, C4 is G3 plus P3 into C3 is G2 plus P2 C2. You get G3 plus G2 P3 plus P3 P2 C2. Now substitute for C2. C2 is G1 plus P1 C1. So you get G3 plus G2 P3 plus G1 P3 P2 plus P3 P2 P1 C1, which is nothing but G0 plus P0 C0. So you get G3 plus G2 P3 plus G1 P3 P2 plus G0 P3 P2 P1 plus P3 P2 P1 P0 C0. Where Pi is AI XOR Bi and Gi is AI Bi for all I is equal to 1 2 3, 0 1 2 3. Problem 4.16. Define the carry, propagate, and carry generate as Pi is Ai, XOR Bi, sorry, Pi or Bi, Gi is Ai, Bi, respectively. Show that the output carry and output sum of a full adder becomes Ci plus 1 is Ci complement Gi complement plus Pi complement whole complement. Sum is Pi Gi complement XOR Ci. Here you have one stage. So the solution is as follows. We know that the carry Ci plus 1 is Ai Bi plus Ai Ci plus Bi Ci. Sum is Ai XOR Bi XOR Ci. If P is Ai plus Bi and G is Ai Bi, then Ci complement Gi complement plus Pi complement whole complement is using De Morgan's law. Ci complement Gi complement whole complement into Pi complement whole complement, which is Pi into Ca plus Gi which is AI plus BI into CI plus AIBI, which is AICI plus BICI plus AIBI, which is equal to CI plus 1. So CI plus 1 can be deduced or calculated from GI and PI when GI and PI are defined as in the question. Similarly, PI GI complement XOR CI is A plus BI, or let's do the XOR first. It's CI into PI GI complement whole complement plus CI complement into PI GI complement, which is CI into PI complement plus GI plus PI CI complement GI complement, which is PI complement is AI complement BI complement, which is CI into AI complement BI complement plus CI into AI BI, which is CI into AI XOR BI complement. PI CI complement GI complement is PI is AI plus BI to CI complement to GI complement is AI BI complement. So this will turn out to be CI complement into AI plus BI into AI complement plus BI complement, which is nothing but AI BI complement plus BI AI complement, which is nothing but AI XOR BI. So this in turn is nothing but CI XOR AI XOR BI, which is simply SI. So if we define PI and GI as we have done in this question, then we can get SI by taking complement of GI, adding it with PI, taking XOR of the result with CI. So here we will have to get P0 as A0 plus A0 or B0. So you have P0 complement here. Similarly, G0 is A0 B0. You have G0 complement here. This is C0 complement. This is C0 complement, G0 complement. This is P0 complement. This is P0 G0 complement. This is C0. We are halfway through, so I'll take a break and come back later. I'll be back in 20, 30 minutes.